Next, exercise 643. The previous analysis video ended with this one, although we did not solve it there. So today we are going to start by solving it. And here we already know we have to prove the parts of proposition 6 for 12 that we did not prove in the text. So it starts with part C. We have already proved parts A and B. So let's first recall what part C says. It says that the infimum of the given sequence, we are given a sequence of real numbers, is less than or equal to its limit inferior, which is less than or equal to its limit superior, which in turn is less than or equal to the supremum of the sequence. Okay, so we start things like this. We have the infimum of the sequence less than or equal to an, the nth term of the sequence or nth element of the sequence, for all possible n, for all n greater than or equal to m. That is because the infimum, being the greatest lower bound, is after all a lower bound, so it will be less than or equal to all the terms of the sequence. Choose any integer capital N greater than or equal to m. Then in particular these inequalities are also true for the index n greater than or equal to capital N, that is the infimum is less than or equal to an for all n greater than or equal to n. So that means in particular we are saying because possibly we have removed some inequalities from this list of inequalities, namely those where the index small n takes the values small m plus 1, small m plus 2, etc. up to capital N minus 1, possibly. Okay. So, okay, what do these inequalities mean now? So that means the infimum of the entire sequence is a lower bound for this set, the set of all an where n is greater than or equal to capital N. These inequalities say this thing. Okay, all the an's where n varies like this are greater than or equal to this infimum, so that means it's a lower bound. And then what will this imply? This will imply that this is some lower bound of this set, so this will be less than or equal to the greatest lower bound of this set. Hence infimum of an is less than or equal to the greatest lower bound, means again infimum of this set. However, according to our notation that we had for these things, This infimum is nothing but a suffix capital N minus. Okay. This implies that the infimum of the sequence, we have shown that this is less than an minus, that itself is less than the supremum of this set. Or to distinguish this n from the varying index here, let's call it m. This n is any chosen integer greater than or equal to m. So if we vary this m like this, then the supremum of all these infima, all of them are infima. So this supremum is greater than or equal to this, obviously, and this supremum is nothing but our limit inferior by definition. Okay, so that's how we get the fact that the infimum is less than or equal to the limit inferior. Similarly, one can prove that the limit superior is less than or equal to the supremum of the sequence. You can clearly see that one has to cross it similarly, doing similar things, but for this one, for this inequality. So we are not going to say anything more about this second inequality. It follows similar to this one. So now we want the middle one. Okay. And for this we will use proof by contradiction. Suppose that L plus is strictly less than L minus. The limit superior is strictly less than the limit inferior. That is, okay, so what is the definition of limit superior? Limit superior is the infimum of this set am plus and the limit inferior we have already seen, it's the supremum of the set of infima. It's very easy to get confused with all these things, okay? So it's better to do things slowly. This is equal to the supremum of this set you can make your own little rules to remember these things. When you have supremum outside here, the objects of which we are taking supremum, they are themselves infima. So when we have supremum, we have minus here. When we have infimum, we have plus here. Right. Now this inequality tells us what? It tells us many things, but among them it says that, you see, this quantity is strictly greater than this, and this is what? This is the greatest lower bound of this set. Since this quantity is even greater than the greatest lower bound, so this cannot be a lower bound of this set. So we accordingly write, since this is greater than the greatest lower bound of For the sake of clarity, for once at least, let's write all the things. M. This is not a lower bound of this. And now that itself has implication. Okay, so this is not a lower bound of this means it cannot be less than or equal to all the elements of this set. At least one element should itself be strictly less than this, because in that way only this fails to be a lower bound of this set. So there exists an integer, say m1 greater than or equal to m such that am1 is strictly less than this supremum. Because of this inequality, this is not a lower bound of this set. Now this inequality again, it says something similar. You see, supremum means what? Least upper bound of this set. This am1 is smaller than the least upper bound. So this cannot itself be an upper bound of this set, since am plus is less than the least upper bound of this set am1 cannot be an upper bound of this set. So, not being an upper bound means what? It cannot be greater than or equal to all the elements of this set. That is, there will be at least one value of capital M for which the corresponding element in this set is strictly greater than this one. So there exists an integer m2 greater than or equal to m such that am1 is strictly less than, oh sorry, see, already I have made a mistake, I think. Yeah, that's why we should be extra careful with these things. So I think I made the mistake here itself. This is not a lower bound of this set. That means at least one element should be less than, okay, so we should have plus here, yes. This is plus, this is plus, this is plus, this is plus, this is minus, yes, now it's okay. We thus have now am1 plus itself is a supremum, and it's the supremum of this set am, okay, am plus I am going to write, so that means it's the supremum of the set. We can write ordinary n is greater than or equal to m1, this is this, and in place of this however is an infimum. It's the infimum of this set an, where n is greater than or equal to m2. Okay, now let m3 be defined to be the maximum of these two integers m1 and m2. Then what shall we have for this m3? Then okay, let us concentrate on am3. First of all, because m3 is the maximum of m1 and m2, m3 is greater than or equal to m1. Okay, so am3 is an element in this set. Hence, the supremum of this set will be greater than or equal to am3, because am3 is an element. Okay, and that is less than the infimum of this set. However, m3 besides being greater than or equal to m1 is also greater than or equal to m2, because it's the maximum of these two. So am3 is here in this set also, and hence the infimum of this set will be less than or equal to the element am3. Do you see that we now have a contradiction? We now have obtained an absurd result that am3 is strictly less than itself. This is not possible. To emphasize that, we write that is am3 is less than am3, which is not possible. Thus, that means the supposition we made, that must be wrong, because whatever we did here, there is nothing logically wrong with the steps. So that means our starting point should be wrong. Thus our supposition that L plus is less than L minus is wrong, and we must have L minus less than or equal to L plus. So that is our middle inequality. And note one subtle thing here. Keep in mind that this L plus, L minus, they are not necessarily real numbers. They can be plus, in any one of them can be plus infinity or minus infinity. So these are extended real numbers. So then how are we, are we justified in concluding that if this is not true, then this must be true? Yes, we are justified in concluding that, because just like the ordinary order relation on the system of real numbers, the extended order relation on the system of extended reals also is one which satisfies trichotomy. That's why for two extended real numbers L plus and L minus, if this is not true, then one of the other two things must be true. So that's how we are getting this, and this is part C. Next we prove part D. Okay, in part D, what do we have to, what is the statement of part D? Let's first recall that. In part D, the statement is this: C is a limit point of our sequence. We have to prove that the lower limit is less than or equal to C and the upper limit is greater than or equal to C. Limit inferior is less than or equal to C, which is less than or equal to the limit superior. This also will be done by the method of contradiction. Suppose that C is strictly less than the limit inferior. It's now time for us to use parts A and B, that is those things. Okay, so let us recall then. By part A, there exists an integer n greater than or equal to m such that before we apply part A, we should perhaps do something not so fast. We need another real number. Keep in mind that things would have been really easy if it was given that L minus is a real number. L minus cannot be minus infinity. That is there. That's because there is one real number C. You see, C is given to be a limit point of the sequence, and a limit point so far we have seen is by definition a real number. So C is a real number, and because L minus is greater than C, so L minus cannot be minus infinity. However, there is still that possibility that L minus can be plus infinity. So keeping that in mind, we cannot use L minus in this way. For example, we cannot consider this quantity. This quantity will become meaningless when L minus is plus infinity. We have not defined things like that. Okay. For us, when we are dealing with extended real numbers, so far what we have seen, we can say which extended real number is less than or equal to which one, and we can negate an extended real number. That much we have gone. Okay, so instead of using L minus, we use something in between C and L minus, and that can always be found. You see, if L minus is a real number, then from this inequality we know that there is a real number lying between C and L minus, and when L minus is equal to plus infinity, then also between them there is a real number. So we write, and the reason why we need an extra real number in between, that will become clear. Okay, let us see the things. Choose a real number C1 such that C is less than C1 and C1 is less than L minus. Note that C is less than C plus C1 divided by 2, which is less than C1, which is less than L minus. Whatever we wanted to do with L minus, now we are doing that with C1, and now there is no problem with this because both C and C1 are real numbers. Okay. Now the fact that this thing C plus C1 divided by 2 is less than L minus allows us to use part A. So by part A, there exists an integer, say m, greater than or equal to small m, such let's keep this for the moment. Such that all the terms of the sequence are going to exceed this number starting from that stage. That is, the sequence eventually exceeds this, such that an is strictly greater than C plus C1 divided by 2 for all n greater than or equal to n. Okay, so in concluding this, we have only used our supposition and part A. So far, note that we have not used the hypothesis that C is the limit point of the sequence. Now we are going to use it. Since C is a limit point of our sequence, so then what will happen? For limit point, what we know is this: if we are given a positive real number and a stage, say that stage is this m itself, then there exists an integer, say n naught, greater than or equal to m, such that the distance between a n naught and c is less than or equal to epsilon. That, in fact, that's the definition of a limit point. Now this part suggests that the m that we are going to choose for our limit point is this m itself. Okay, that is one stage we have. But what is epsilon? This epsilon now we will cleverly choose using this fact that c1 is greater than c, so that c1 minus c is a positive real number. We won't choose epsilon equal to c1 minus c, but rather c1 minus c divided by 2. You will see why. Since c is a limit point of this, there exists an integer n naught greater than or equal to m, such that this is less than or equal to c1 minus c divided by 2. Okay. Okay, now what is the consequence of all these things? Then an naught minus c is less than or equal to the absolute value of an naught minus c, which is less than or equal to c1 minus c divided by 2, or this, of course, we know any real number is less than or equal to its absolute value, where we have equality when the number is a non-negative real number. If it is negative, then we have strict inequality. Now adding c on both sides, we get an naught less than or equal to c plus c1 minus c divided by 2, and if you simplify this a little bit, you get 2c minus c, so that means c plus c1 divided by 2. Now see what we have got. So an naught is less than or equal to c plus c1 divided by 2. However, at the same time, we have this fact also: an is strictly greater than c plus c1 divided by 2 for all n greater than or equal to m. And because our choice of n naught is like this, so this inequality is also true for n naught. However, since n naught is greater than or equal to m, we also have an naught strictly greater than c plus c1 divided by 2. This is a contradiction. So our supposition is wrong, that is this is wrong. So we must have L minus less than or equal to C. Similarly, one can prove that C is less than or equal to L plus. These parts that we are leaving by writing similarly one can prove, you please try to do these things and see whether you get a similar result or you get stuck somewhere. If you get stuck, please let me know. Okay, so that is part D. Then we move to part E. In part E, we have to prove these things. If our, say, upper limit, the limit superior, is a real number, then this is a limit point. Limit point of our sequence. Similarly, we have the statement for the limit inferior. If that is a real number that is finite, then it's also a limit point of the sequence. We are of course going to prove this one. If you want, you can prove the other one also and write similarly one can get this one. We choose to prove this one. So we start by assuming that the upper limit belongs to the set of real numbers. Now we want to prove that L plus is a limit point. So we choose the things that we need to show that a given real number is a limit point of a sequence. Choose a real number, a positive real number epsilon, and any integer, say n, greater than or equal to m. Okay. Since, right, so because epsilon is positive, L plus will be less than L plus plus epsilon naturally. And now note that L plus is a real number. Now it cannot be infinite. It is neither plus infinity nor minus infinity. So this sum makes sense. Okay, it is meaningful. So since this is less than this, by part A, there exists an integer, say k1 greater than or equal to m, such that all the terms will be less than or equal to L plus plus epsilon. I think that's what we have in A. It is somewhat difficult. Yes, that is the thing. These things are so confusing. I mean, slightly difficult to remember always. So because this extended, this is now a real number, however it's also an extended real number, this is exceeding the limit superior. So there will be a stage such that from that stage onwards all the terms of the sequence will be less than or equal to this. Oh, not just simply less than or equal to, but in fact strictly less than. That's what we have in part A. So such that an is strictly less than L plus epsilon for all n greater than or equal to k1. On the other hand, since L plus minus epsilon is less than L plus, this is the situation where we would use part B. So there we have something happening eventually and uniformly after some stage. Here that is not, that will not be the case. Here something will happen infinitely often. Since this is less than L plus, by part B, there exists an integer, say n naught, and the stage that we are choosing after which this thing is going to happen is this k1 itself. Will this be enough for our purposes? Let me just think for a moment, okay, whether I am really getting what I want to get or not. Oh, if I simply choose this to be k1, then that may not be enough for what we are trying to show. Instead of taking k1 here, let us take maximum of k1 and n. Such that an naught will be strictly greater than this. Okay, let me just quickly see if this part is correct. I have started by assuming L plus to be a real number. Then, in order to show that it's the limit point, I have chosen a positive real number epsilon and any integer n. Okay. Then, because L plus epsilon exceeds the limit superior, so there will be a stage. Starting from that stage onwards, all the terms of the sequence will be strictly less than that number which exceeded the limit superior. Okay. On the other hand, L plus minus epsilon, it is not exceeding L plus, and in fact it is less than L plus. So by part B, we can find an integer n naught greater than or equal to any pre-assigned stage, and that pre-assigned stage here we have chosen in this way, okay, which is the maximum of k1 and n, such that the corresponding term an naught exceeds this big number. I mean, you can think of this as stronger than L plus and this as weaker than L plus. Okay, so an naught exceeds this weak number. Okay. Now, okay, so what do we have now? An naught is strictly greater than L plus minus epsilon. Can we take n naught here in this inequality? We can now, because if we, you see here in this inequality, n naught is greater than or equal to maximum of k1 and this in turn is greater than or equal to k1. So n naught is greater than or equal to k1. So accordingly we write, note that since n naught is greater than or equal to the maximum of k1 and n, which is greater than or equal to k1, we have this an naught strictly less than L plus epsilon. Thus, L plus minus epsilon is less than an naught and an naught is less than L plus epsilon, or the absolute value of an naught and L plus, I mean an naught minus L plus is less than epsilon. Okay, we have shown that this distance is less than epsilon. And what is this n naught? This n naught, from this choice we see that this is of course greater than or equal to k1, but at the same time it is also greater than or equal to n, and this n was our stage after which we wanted this to happen. So such an n naught has now been found. Note that, so we mention that extra fact, n naught is also greater than or equal to n. Hence, this is a limit point of our sequence. Similarly, one can prove that the lower limit, the limit inferior, is a limit point of our sequence provided it's also a real number. It's a finite extended real number. So this is part E, and finally we have part F. Okay, so in part F, this is arguably the strongest part of this proposition. It says that if we have this, if our original sequence is convergent and it has the limit c, which of course is a real number, then the limit inferior and limit superior are both equal to c. And conversely, if these are equal and both of them are a real number, then the original sequence is convergent and it converges to that common real number. So we first prove this. First, assume that our sequence is convergent to the real number C. Then so now recall the result in this section itself, where we proved that limits are limit points. So that means C is a limit point of our sequence AN, and also not just that, C is the unique limit point. What is the number of that result? Proposition 645. C is the unique limit point of our sequence. This is one thing that we can immediately say. On the other hand, by corollary 6117, the sequence is bounded. Corollary 6117 says just that every convergent sequence of real numbers is bounded. That was corollary 6117. So this is bounded means what? So its supremum and infimum both will be real numbers, will be finite. Hence, by part C, these are finite, that is, these are real numbers. What has happened here? In part C we have proved this now. Boundedness of our sequence means these are real numbers. So the other terms which are trapped in between these two things, they are also forced to be real numbers. But now, because these are real numbers, by part E, they are limit points. What we have proved here just now. Hence, by part E, L minus and L plus are both limit points of our sequence, which has the unique limit point C. So that's why they have to be equal to C. Thus, okay, so we have got one half, we have got this implication. Now we will prove this one. Conversely, assume that these two are equal and they are equal to C, where C is already C has already been given to be a real number, some real number, right? We want to now prove that our sequence converges to C, so we need an epsilon okay. Since so this is now the perfect place to use part A, since L plus is strictly less than L plus epsilon, which is nothing but C plus epsilon, by part A, there exists an integer k1 greater than or equal to m, such that an is strictly less than this, that is C plus epsilon, for all n greater than or equal to k1. This number is in my terminology stronger than the limit superior, so the sequence will be less than this strong number eventually, starting from this stage. That's what part A says. Also, since C minus epsilon, which is L minus epsilon, that is less than L minus, note that. That's why we can again apply part A. By part A, there exists an integer looking at these things. Okay, let me just first write the thing, otherwise I will lose track of it. There exists an integer k2 greater than or equal to m, such that the sequence exceeds this weaker number, weaker than the limit inferior, for all n greater than or equal to k2. These things are going on somewhat. We are not looking at these things. Don't think that we have had to think a lot about these things to come up with some original idea to be able to write solutions like this. No, if you think about these things somewhat carefully for some time, you will get these things quite easy. However, despite this easiness, things are somewhat messy. You have to really get down with the inequalities, you have to guess the estimates, do this and that to get the result. This sort of messiness is in some sense absent in complex analysis, which is in some sense many people won't feel this, but complex analysis is more beautiful than real analysis. The restriction that real analysis has, that it always has to remain on the line, is not there in complex analysis, and this has implications. We will see these things when one day we start that. So there exists an integer for which this happens. Now let k3 be the maximum of k1 and k2. At first these arguments will seem like impossible to come up with. However, the more you see them 2-3 times, you will see that there is a pattern of things, of how the things are appearing. When you have two stages like k1 and k2, it's most often that you have to consider a k3 that is larger than or equal to both of them. So that's why we choose maximum. You see this occurring many times. So from those things you can guess what to do next. Now let k3 be this. Then for any n greater than or equal to k3, we have what? Because k3 is greater than or equal to k1, so that n, for that n we will have this inequality true, and also because n is greater than or equal to k2, this inequality is also true for that n. So that means c minus epsilon is less than an, which is less than c plus epsilon, that is the absolute value of an minus c is less than epsilon for all n greater than or equal to k3, and this is convergence. It proves that the sequence an converges to C. Okay, so that completes part F and it completes this solution. Next, prove lemma 6 for 13. That is the comparison principle. So let's first recall the statement. This is the statement. We are given two sequences of real numbers for which these inequalities are true. An is less than or equal to Bn for all the possible indices. So you can say that the sequence Bn dominates the sequence An term-wise. Then the infimum of the sequence An is less than or equal to the infimum of Bn. Let's not write the variation of n because it's just for the sake of recalling the statement. Supremum also is less than or equal to the supremum of Bn. Then limit inferior is less than or equal to the limit inferior of Bn, and similarly the limit superior of An is less than or equal to the limit superior of Bn. So we are not going to prove these things, but some ink is needed. Okay, so these things are given. So we are going to start like this. Note that the infimum of our sequence is less than or equal to An, that is given to be less than or equal to Bn, that is less than or equal to the supremum of Bn for all n greater than or equal to m. What do we see from these inequalities? We see two things, among other things. You see, as small n is varying in this way, this quantity, this infimum, is less than or equal to all the Bn's. That means this is a lower bound of all the Bn's, and just like that, the other thing is that this is an upper bound of all the An's. Hence, and this is an upper bound of all the An's. In other words, this is a lower bound of the sequence Bn, and this is an upper bound of the sequence An. So the greatest lower bound of Bn will be greater than or equal to this, and the least upper bound of An will be less than or equal to this. Hence, so we at once write the things. Okay, we are not going to delay this any further by writing more details. So this is less than or equal to, this is one lower bound, and this is the greatest lower bound of all the Bn's. And just like that, the least upper bound of all the An's is less than or equal to this some upper bound. This is an upper bound of this. Okay, so that means we have got this inequality and this one. Now next we look at any one of these limit superior or limit inferior. Let us choose this limit superior. Okay, limit inferior we will just say one can do it similarly. Next, for any integer n greater than or equal to m, we have okay, here for limit superior, what do we need to do? What is the limit superior? First of all, limit superior is the infimum of a set of suprema. Okay, so whatever we did here, we are now going to do again, but for the indices greater than or equal to capital N. Yes, so that means infimum of a n greater than or equal to capital N is less than or equal to an, that is less than or equal to bn, that is less than or equal to supremum of bn for all n greater than or equal to capital N, which is easy to understand. Whatever we did there, now we are again doing, but the indices are starting from capital N instead of starting from small n. Now this is what, we have taken infimum, no? Will that help? I don't think we need this part, however. This is not needed. So instead what we write is this: an is less than or equal to bn, and bn is less than or equal to the supremum of bn as n varies like this for all n greater than or equal to n. Okay, so we have removed that infimum part. We don't need that, I think. We will see. Now what is this? This is nothing but b capital N plus, it's that supremum. Okay, hence b capital N plus is an upper bound of this set we can clearly see that from here an is less than or equal to this. Thus what is an plus? An plus is the supremum of this set, which is the least upper bound. And this least upper bound is less than or equal to this one, which is some upper bound. And all these things are happening for any integer capital N. So we can vary that N also. We thus have an plus less than or equal to bn plus for all n greater than or equal to m. This implies what? Right. So that means infimum of all these an classes as capital N varies, which is, let's keep some space, is less than or equal to an plus, which is less than or equal to Pn plus for all n greater than or equal to m. This is easy to understand because this is the infimum of all the an classes, so it will be less than or equal to each one of them, and consequently this will be less than or equal to each bn plus for all possible values of capital N. This, however, is what? This is nothing but the, I don't have space for writing this now. Let me write as tightly as possible. This is nothing but the limit superior of the sequence an. It is the upper limit of the sequence an. Okay, and that we have shown is less than or equal to all the bn pluses. Thus, is a lower bound of this set. So we have, so this is one lower bound. This will be less than or equal to the greatest lower bound of this set. So we have limit superior of an less than or equal to the greatest lower bound means infimum. And that in turn is nothing but the limit superior of the sequence bn. So we have got that one inequality. The remaining one, that is this thing, limit inferior of an less than or equal to can be similarly proved. So this is our solution, and this completes means once provided that one proves this, the proof of the comparison principle. Okay. Next, six, 4, 5. Next, we have to prove that squeeze lemma, or what is also sometimes known as the sandwich theorem, although I am not sure whether the corresponding result, you recall squeeze lemma, there are three sequences an, bn and cn, and bn is trapped in between an and cn. If an and cn have a common limit, if both of them are convergent and they converge to a common limit, then bn is also forced to converge to that limit. There is another similar thing for functions and their limits, that is known as sandwich theorem. This one, however, I am not sure if it is also called sandwich theorem, the sequence one. However, the author is calling it the squeeze lemma. Specifically, the statement is this. Oh, I have not written the exercise itself. Use lemma 6 for 13. That means the comparison principle, what we have proved just now. To prove corollary 6 for 14. So this is the statement of this corollary. Three sequences of real numbers are given to us. And they satisfy these inequalities. an is less than or equal to bn, bn is less than or equal to cn for all the indices. If an and cn are convergent, and have the common limit L, then Bn is also convergent and has that same limit L. That's what we have to prove now. And we somehow have to use the comparison principle, that is these inequalities. Since an is less than or equal to bn and bn is less than or equal to cn by lemma 6 for 13, we have these things. Limit inferior of an is less than or equal to the limit inferior of bn, which is less than or equal to the limit inferior of cn. And just like that, these inequalities are also true, involving limit superior. Okay. Now we use this part. Since limit of an and limit of Cn are both equal to L by part F of proposition 6 for is that 12? Yes. Limit inferior of an is equal to limit superior of an is equal to L, which is also equal to limit inferior of Cn, and that is also equal to limit superior of Cn. So we can now use these facts here. Thus, L is less than or equal to the limit inferior of Bn, which is again less than or equal to L. Both of these things are equal to L, and L is also less than or equal to, won't have space here. Limit superior of Bn less than or equal to L, that is L is equal to the limit inferior of Bn, that is equal to the limit superior of Bn. Hence, by part F of proposition, it's neither theorem nor lemma, proposition 6, 4, 12, Pn is convergent and its limit is also equal to L. So that is the squeeze test. It completes the solution and proves the corollary. Then let us solve another one. 6, 4, 6. There are so many things in analysis. We are still in the theory of sequences of real numbers. We still have to see continuity of functions, differentiability, integrability, and that too we are trapped in the world of functions of a single real variable. After that, in volume 2 we have functions of possibly many real variables. After we do these things, we will be able to start, well, not after finishing all these things, but On the way, somewhere we will start complex analysis, but then there is functional analysis. Okay, let us go ahead and see how far we can go. Exercise 646. Give an example of two bounded sequences. AN and BN such that AN is strictly less than BN for all positive integers n. So here the index starts from 1. It does not really matter where it starts. For definiteness, I think the author is taking 1. But that the supremum of AN is not less than the supremum of Bn. Okay. Explain why this does not contradict what? Contradict the comparison principle. The example is rather easy. Consider AN as we are defining AN to be minus of 1 over 2n minus 1. And Pn is defined to be minus of 1 over 2n for all positive integers n. So let these be the sequences. So that means if we write the terms of the sequence AN, the first term will be what? We would put n equal to 1, so minus 1. Then the second term will be minus 1 over 3. The third one will be minus 1 over 5, and so on. And if we write the terms of the sequence Pn, then it will be minus 1 over 2, minus 1 over 4, minus 1 over 6, and so on. Okay, so Yeah, now in this way if you write, then the thing is much more clear. You can see some things from here. One is that these inequalities are true, which you can see in general also. -1 is strictly less than -1/2. -1/3 is strictly less than -1/4, and so on. One more thing is that the suprema of both the sequences are equal to 0, least upper bound, which you can using analytic arguments you can easily prove that the supremum of both of these things are equal to 0. So the one supremum is not less than the other supremum. Let's now write these things in general. Then we see that anything else, both of them are also bounded sequences, because from that those two lists you can see that both of them are greater than or equal to all the terms are greater than or equal to -1 and less than or equal to 0. Or you have this actually, for all n greater than or equal to n, bounded by 1. So we see that an and bn are both bounded by 1. An is strictly less than bn for all n greater than or equal to 1, and this. Now comes the question of why this does not contradict the comparison principle. The above example does not contradict lemma 6 for 13, because the lemma says that for an less than or equal to bn for all n greater than or equal to 1, supremum of an is less than or equal to supremum of bn. That means supremum of an is either strictly less than the supremum of bn or the supremum of an is equal to the supremum of bn. That possibility is also there, and that's what we have here. We have got equality. So that's why the comparison principle has not been violated, and this completes the solution. There are other exercises also, which however we will do next Sunday. And okay, so I'm ending this video here itself. We have in fact completed one cycle, we have reached graph theory. So that means the next video should be on group theory, again from Herstein's topics in algebra, which however, instead of having it tomorrow, I will do it day after tomorrow, that means on Tuesday. So that's just it for tonight. If you want to comment on these things, you can write in the comment section below. So see you day after tomorrow on Tuesday. Tuesday means you can see the video on Wednesday, or it depends on the time zone. I don't know which one of you will get it when. So anyway, see you in the next video. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.